Thank you for joining us for this look at the path to STEM innovation. I'm Francis Vigent, CEO here at KnowAtom. To introduce you to KnowAtom and what KnowAtom is, we are an organization focused on higher order thinking, specifically critical thinking skills, the skills to create, evaluate, and analyze the way a scientist or engineer would. In order to do that, we think that science and engineering, or STEM, science, technology, engineering, and math, is really the best context to teach those skills to children from kindergarten through grade 12, not so that every child will graduate and be a scientist or engineer, but so that they'll be well equipped for any college or career of their choice. With that in mind, we help educators and school districts to be able to transform their classroom into a place where students can actually be scientists and engineers, learn hands-on, and engage in the practices of science and engineering. That way, if they choose to pursue sales or marketing, go to college, or even pursue a terminal degree in science or engineering, they are ready with the skills to be trainable for whatever future they choose. And as part of that, we like to engage in professional development, and this particular session about the path to innovation is one of those professional development series. I'd like to introduce our special guest today, Joshua Lederman. Josh is an undergraduate student in engineering physics at the College of Engineering at Cornell. We're especially excited to have Josh here with us today because he represents the first generation of KnowAtom elementary school students to have reached college age. We're encouraged to know that he's found a passion in STEM and is pursuing an engineering degree at Cornell, specifically engineering physics. Welcome, Josh.
It's great to be here.
And we appreciate you joining us. So, thinking about kindergarten through 12th grade and now to undergraduate engineering, I wanted to bring up this diagram to sort of clue our audience into the relationship between science, knowledge, engineering, and technology, especially as it exists today with the next generation science standards, that science is considered knowledge from experimentation, that scientists ask questions and they actually expose the underlying theories that, I guess, govern our world. Engineers use that knowledge to solve problems by prototyping and testing technology, which then gets scaled up to help us all and improve our lives, math being sort of at the center of it all, helping us communicate. So I wanted to get your thoughts first and foremost about why you chose engineering in the first place, Josh.
I would say I chose engineering because I always, from a very young age, I like to understand how stuff worked. I like to learn how people have done stuff before, to design my own things, even if using the type of kits you learned with electricity and magnetism, simple circuits. That was at a young age, and I've always enjoyed that, and so I decided to pursue basically a very in-depth understanding of how stuff works in engineering at Cornell.
So as you were sort of transitioning through elementary, middle school, and then high school, you did graduate valedictorian of your class. Why did you choose Cornell of all colleges of engineering? Was there something special that stood out?
Well, first and foremost, Cornell has a great engineering program, but I really liked it because of the opportunities I saw there, both in terms of kind of the academic quality and also the ability to apply the type of things I'm learning in either research or, as we're going to talk about, in project teams where you can actually build things using what you're learning in class.
So it sounds like the program you're a part of really brings this relationship between science and engineering, the knowledge and the technology piece together in an applied way. I noticed that Cornell talks about breaking the rules to encourage independent thinking. What does that mean to you in the context of your program?
I would say that it means to me that to come up with do things the ways you haven't done before, to come up with new ways of achieving a task which don't conform to kind of the expectations or the practices you might have learned in learned about in classes or in kind of the typical way of doing things. You often the best way of fixing a problem is something that has been done before, and that it will you have to think outside the box. You have to think of new ways to do things in order to innovate and come up with devices that can solve problems.
So thinking about that focus, can you explain a little bit about your major? You're studying engineering physics, which basically sounds to me like taking that knowledge and somehow turning it into technology. How does that work? What is that major about?
So engineering physics is kind of a combination between a theoretical understanding of physics and applying that theoretical understanding. It kind of includes you have to have a broad understanding of kind of the concepts of physics, the physical laws, but also the majors focus on how you can use those laws. For example, nanoscience involves a combination of aspects from electricity and magnetism, material science, even kind of mechanical engineering, and it's in order to understand those things, you have to have a broad understanding of physical phenomena, and that I think is what engineering physics is all about.
So even outside of your degree and sort of your program classes, you've elected to kind of take it a step further, and Cornell's one of those unique places, I think, that when most people think of undergraduate college experience, they think about joining sports teams like football, baseball, lacrosse, maybe swimming, and so on. But top engineering schools like Cornell's have made a sport of team research and problem-solving competitions, and one of those is the Cornell University Autonomous Underwater Vehicle Team, CUAUV, which you're a part of. Can you explain a little bit about how this maybe takes some of your major focus to the next level and how research is a competition here at the university level through CUAUV?
Yeah. I see CUAUV as a kind of a bunch of people working together in order to create a project by the end of the year. Instead of kind of the traditional team sports where you're focused towards kind of the next competition, you're competing with other teams throughout the year, I feel that CUAUV, the whole year is focused toward one objective, where we are constantly thinking of ways of accomplishing that objective. You have a bunch of different people, each one who's working on some component of the project, so that everything can combine to produce something that is, I guess, more than the sum of its parts, something that can, I guess, compete at the end of the year, something that's kind of, it's an innovation. It's a new device that is different from anything that's come before.
I see. So in comparing CUAUV with sort of a traditional college team competition like baseball or something, do you have sort of perhaps instead of just sort of the championship at the end of the year, like we might think of with football or baseball, something like that, do you have perhaps milestones within the year, smaller competitions or sort of testing, anything like that that goes on a more local level?
Yeah, there definitely is kind of a structure, a schedule where each kind of step throughout the year, we start out with more electronic designs using design software. Then we go through printing for electrical team, which I'm on. It's printing circuit boards. Then we go into test the circuit boards, then they get integrated into the new sub. So it all builds up throughout the year toward the end competition in a way that I feel doesn't really work For traditional team sports, it doesn't really work that way. And I really like that aspect of CUAUV.
Oh, that's great. So just taking a look at this, this is the CUAUV team, this year's team. I wanted to take a closer look, though, at what you're actually creating. So an autonomous underwater vehicle is a robot. And correct me if I'm wrong, it's a robot that it's not tethered sort of to anyone. You're not sort of controlling it by remote. It has to operate on its own autonomously. Can you take us through what these robots are supposed to do and how that competition's structured at a high level?
So there are the competition occurs once every year at the end of July. So it's basically every year the team creates a new robot for the competition. And while the robot tends to kind of improve on the last year's robot, it is always a new design. You can see from the image there are kind of three different devices along the outside of the robot. You see the thrusters, which allow it to move it around, sensors such as the cameras toward the right side, which allow it to get input from the surroundings, and also actuators. You can see a claw kind of in the center, as well as a funnel toward the right, which allow it to interact with the tasks. There are something like 5 tasks every year, which the robot is designed around. They involve visual recognition, manipulation of objects, shooting torpedoes, and the like things that a typical underwater vehicle will have to do in, for example, a more applicable surroundings such as underwater exploration. The robot basically has to do it entirely autonomously. It has to figure out where it is, interact with surroundings, and accomplish the objectives without any human input, which involves a lot of advanced software within the robot.
I have a few pictures actually from the competition that I believe occurs in San Diego. Could you tell us a little bit about that? Here's the robot being dropped into the water here.
So yeah, you can see the swimmer on the right is actually not a member of CUAUV. He is, or she I guess, is a member who works for the competition, because we are not allowed to have any contact with the robot after it's put in. The swimmer starts the robot, then they follow it around, usually taking video, and watching as it tries to accomplish the objectives. You can see it looks very impressive underwater. I think we have some pictures of some of the tasks. Here you see claws have to pick up these objects, actually has to recognize which are which. I think these are actually made out of Kinects, and move them around. Some of the other tasks involve picking up objects from the surface and moving them around using the funnel at the end I punched out earlier. This was this task right here. And they're also shooting torpedoes and stuff like that, as I talked about before.
So basically there's a series of obstacles that once this robot's in the water and positioned by the competition judge or sort of mediator here, it has to go autonomously through the water, and it looks like this is in an environment that's designed to mimic the ocean. And I think, did you say this is a Navy test facility?
Yes, it's a Navy testing facility called Transtech in San Diego.
So it'll maneuver itself through the water, and then there's this series of different tasks that it's going to have to do all on its own. So kind of, I guess, thinking about that, there's basically kind of 2 levels of success. First and foremost, you have to get something physically together. It has to survive in the water, and then it has to go through and be able to complete all of the different tasks. So there's kind of completing the challenge of physically creating an autonomous vehicle, and then there's sort of this second task of actually winning a competition. And these are Thor and Loki I believe the 2015 or 2016 CUAUV autonomous vehicles here. What separates basically, the first part from the second part, the completing the challenge from winning?
I would say that, well, of course, you have to be able to get a working robot in order to win. But the fact that you actually have a working robot is hard enough. I would say that usually robots do not manage to complete all the tasks or even most of the tasks every time. So just having a robot there, and which is attempting at the task, is a pretty major objective. As you can see, we have 2 different robots this year, which is the first for CUAUV. And what we're trying to do is have 2 different robots so that they can focus on 2 different categories of tasks, because it's so difficult for one robot to complete every single task on its own. So it kind of shows how much it means to be able to complete a task at all, and completing enough tasks is basically all you need to do to win.
So thinking about, often in education we talk about 21st century skills, and the idea of completing a task. In this case, it's an extremely nuanced task. It's actually a series of tasks and different systems that have to come together in order to accomplish each of the challenges within the competition, but kind of unified as one autonomous vehicle. How does the team, the CUAUV team itself, take shape and organize to get all this work done?
I would say that the CUAUV team tries to kind of segment the different parts and needs for the sub to work into. They kind of divide them into separate tasks for different people. So we have 4 sub-teams, which I'll be talking about in a little bit, and then which each have different major high-level tasks that are very separated. And within each sub-team, the tasks tend to be separated as well. For example, I'm on the electrical sub-team, and each member has an electrical board that they have to design and build, which has to interact with other electrical boards, which also have to interact with the overall sub. So overall, we have to communicate. We have to make sure that our part's going to work with the other parts of other people on the sub team, as well as fitting into the overall design of the sub, which basically involves working with the other major sub components of the AUV.
So you mentioned communication, and it seems like communication and collaboration go hand in hand. Can the CUAUV team operate without those skills? Or I guess maybe the broader question is, where do those skills come from if that's what makes a good team member? Is that sort of a life skill thing?
Yeah, well, communication and collaboration are definitely very important on the team, because problems always come up, and if you're not constantly making sure that whatever changes you're doing to fix the problems will work with everything else that's going into the sub, then you'll end up with components that don't work together. And so I've always had to make sure what I'm doing is working with what other people are doing, and with kind of the idea of the overall sub. And I feel as though these are the type of skills you're learning at CUAUV. These collaboration and communication skills are definitely important skills. And it's really great to be able to be on CUAUV and get experience doing the types of things you need to do, for the rest of your life, basically, especially in a career.
So could you take us through a little bit of kind of the timeline for this year's team and some of the subsystems? And I've pulled here some stats for the fall 2015 team. You have 46 team members from 10 majors, and this is the 16th year of CUAUV. So it seems like you are building on that body of knowledge from all those prior teams. You've got 2 vehicles in development. Can you take us from here and just tell us a little bit about, how the team evolves from one year to the next, and then we'll go through maybe those 4 sub-teams.
I said before there are 4 sub-teams, and each sub-team that has its own process of finding new members, and usually what they do is they just look for members who are interested in a particular area. So the electrical team, for example, is primarily looking for ECEs, but I have kind of the example of where they welcome other majors who are also interested in electrical and computer, the electrical engineering you need to be part of the team. I'm an engineering physics major, and so the other teams generally have their preferred majors, but it tends to be more diverse than you might expect. And then you can see here these are the new members. So generally, many of the members stay. Some of the members spend a year, then they go on to do research. But kind of from year to year, you always have a certain amount of continuity. And
so it seems like so you have a core group, and then each year you have some new members that join that core, and then they break down into these 4 different sub-teams, right?
Yeah. So to talk about sub-teams, we have the software sub-team. I mentioned before how important it is for the sub to be able to understand where it is, understand what it's doing, find things, and so that's basically what software is dedicated around, creating code, programming to allow it to move around, or allow it to interact with obstacles, and allow it to figure out the higher order what tasks to complete, what order to complete them in, what to do if it does not complete a task, stuff like that. And so kind of the highest level of organization for the sub.
So the software team is basically sort of the brains and programming of the autonomous vehicle. So that must connect to this team, the mechanical sub-team, pretty closely.
Yeah. Well, mechanical is basically I guess if we're continuing with the analogy, it's the body, it's the muscles. They deal with the thrusters, the structure, making sure that the sub is sealed so that the electrical equipment doesn't get wet, which is kind of important. And it works to make sure it does stress testing. It does all sorts of things to make sure that the sub is mechanically able to complete the tasks. And so, of course, the software sub-team has to take into account the capabilities of the mechanical team, though it doesn't directly control any of the sensors, as I'll talk about next. So the electrical sub-team.
I was just going to ask, so with the electrical sub-team and the mechanical sub-team, is there kind of a hierarchy here where you have sort of software being the brains, the mechanical sub-team being the body as you described it, and this is your group you mentioned here, the electrical sub-team, what's your job, where does that fall in relation to the other 2?
Well, I guess you could call the electrical sub-team the nerves. It's what they control the power to all the devices, as well as interacting at the lowest level with the sensors and with the thrusters to make sure that they basically serve as kind of the level between the highest order thinking of the software team and the kind of mechanical capabilities of the sub. They basically allow the computer to control the individual devices.
And you mentioned that most of the team members are ECE. What does that stand for?
That's electrical and computer engineering.
I see. So that's their major, and they may have minors in other areas. You said, right?
Yeah. Yeah. Well,
and to tie it all together, you mentioned there's an even more diverse, perhaps, team than some of these other more specialized sub-teams, which is the business sub-team. what is their roles and responsibilities? How do they fit in with the others? And what is some of that diverse experience?
Business does it does pretty much everything else. It does financing. It does it makes sure that CUAUV is capable to compete in the competition. It produces the various documents and presentations CUAUV needs. It basically makes sure that one of its most important responsibilities is raising money, doing crowdfunding, getting sponsorships, stuff like that. It makes sure that basically CUAUV can exist and that it is up to date with everything that's going on. And so, of course, it kind of the water in which the submarine swims is kind of a bad analogy, but it makes all the other teams possible.
So, in a course of a year, what sort of fundraising in total does the team have to do to be able to exist, sort of as a ballpark?
So, many of the things, kind of the most expensive things we get are through sponsorships. Though it does, we just finished a crowdfunding campaign to raise money for other aspects of the team. I'm not entirely aware of everything that it has to do, but I'm sure that it has a lot of responsibilities in order to make sure that we have the type of funding we need to create what's a relatively complicated and a very advanced sub.
So as a bunch of college students, how do you, how does this team affect your quality of life? This is not, well, I believe you get some class credit for this. It's kind of a quasi-class because it's in addition to your programming that's part of your major and the classes that you have to take in order to graduate. So, is this like a lot of 4 a.m. Kind of meetings? How does that work? How do you function?
So, typically, you have 1 or 2 meetings a week. You're spending time, maybe 5-6 hours a week working on the sub. It's kind of like another class to a certain extent. So, of course, I guess this kind of fits in with class, but you're spending occasionally late nights working up to 2 a.m. to finish things for the deadline. I would say CUAUV it involves a lot of work. It involves a lot of commitment, but it's a very redeeming experience, I guess you could say. It gives you a lot back.
So I want to kind of circle back to sort of elementary, middle school, and high school, and kind of fit your experience now kind of into focus with those other experiences, and ask you, now that you're an undergraduate in a College of Engineering, with just a semester in, do you feel like you can put your thumb on any differences in the approach to learning as you compare this year's experience so far at a college level with last year or prior years, maybe kind of lumping them together, saying K12? What's the difference to the approach? Is there a difference?
I would say that my experience with high school has been that there's a certain expectation of this is what you have to know. You have to be able to do this, this, and this. You have to, by the time you graduate, there are certain skills you have to have. Whereas college is much more like you're doing what you want to do. You're doing it because this is what you're interested in, and the class you're actually trying to learn the material. Whereas you learn the material for the sake of understanding it, rather than in high school, much of there's a sort of expectation that you should be able to do well on a certain end of your test. That's the kind of standard for success, and that's what you're learning the material for.
So it sounds like there's a bit of a difference in the purpose of learning this year versus perhaps prior years. It sounds like this year has been very much applied, and maybe in prior years it's more trying to gather knowledge to meet a benchmark test or something like that. Is that accurate?
Yeah, I'd say that's accurate.
So when you think of something like critical thinking, creating, evaluating, analyzing, do you feel like, let's say, the CUAUV team itself, that competition and those types of experiences, which it sounds like your major represents as an engineering physics major, but even more so at another higher level with CUAUV, does it represent something unique, being able to pull these different areas of critical thinking together? And I pull up this diagram because with the next generation science standards, one of the things that's being talked about right now a lot is the idea that lower order thinking, just remembering, understanding, applying, isn't enough, and in fact it's those higher order thinking skills, creating, evaluating, analyzing, that happen simultaneously, that are the direction that states should go in with their kindergarten through grade 12 curriculum and experiences. So, how does that make sense? Is that a good direction for K12? Does CUAUV represent something that's unique even at a college level in this sort of higher order thinking context?
Yeah, I would say that, CUAUV is basically kind of represents the creating, evaluating, analyzing aspects of thinking. It's basically where you're creating a project and trying to make it work, which is basically involves all three of those things, whereas in high school class, or in a college class even, you definitely do plenty of remembering, understanding, applying, and you can dip into or even go somewhat far into the creating, evaluating, analyzing thing, but you always have to return to kind of lower levels, whereas CUAUV kind of represents learning things entirely in the context of creating, evaluating, and analyzing in pursuit of kind of the AUV as the end goal.
So thinking about elementary, middle school, high school, and then on to college, we go through all of this training for a good chunk of our lives with the idea that we want to do something with that, and it sounds like CUAUV is an opportunity while you're in school. Maybe some people might do internships, but CUAUV is an opportunity to apply even before an internship and create something and see its performance. I noticed that, and you mentioned this a bit earlier, the Cornell University Autonomous Underwater Vehicle Team is sponsored by a number of national and international STEM companies, companies like Shell, ExxonMobil, GE, and many others. Why, what's the connection? Why should these national and international STEM companies who rely on producing STEM innovations invest in your team's work? And what's the broader hope, I guess, as you all emerge from the team, from the college?
I would say that the companies that rely on producing STEM innovations, well, there are people producing these innovations, and those people come from colleges where they have gained experience in teams like CUAUV. It's the type of people that CUAUV produces, the people that go through project teams that are most capable of producing the innovations that these companies, that are the basis of these companies. And I feel as though having the type of STEM education that CUAUV exemplifies is really important for these companies. People who have that education are really important for these companies in order for them to be successful and to continue to produce innovations.
So it sounds like that connection between those higher order thinking skills, the creating, evaluating, analyzing, when you can execute those, whether you want to call them soft skills or whatever, in line with real technical skills, the knowledge of the disciplines themselves, that's a real recipe for success when it comes to workforce development, because you're primed as the people who make innovations or the future innovation makers for these companies to be trainable, but also to deliver on the promise of the companies themselves and their vision and mission.
Mm-hmm.
So thinking about that, I guess for K-12 educators, one of the things that we're often discussing is, to this point, many states' science standards, so what sort of those benchmarks are for proficiency at, kindergarten all the way through grade 12, have been based solely on a student's ability to memorize and recall facts in most states. Do you think that's adequate? And to kind of give that maybe a little bit more context, there's this kind of traditional model that memorize and recall structure sort of forms, and it's what you see here. It's the idea that there's all this content, the facts to be known, and that's out there, and it has to flow through a teacher who is kind of that content expert who demonstrates the phenomena and models the facts and explains what things are all about. And students, and I think this is some of what you had described a little bit earlier, the student's role in that traditional model is to recall the facts, repeat the demonstrations, or be able to summarize the phenomenon to show that they've learned something. Does that traditional model, does it fit? Is it adequate?
I would say that the student, in order to really understand the material, they have to be able to, I guess, access the content for themselves. They have to be able to experiment, to learn. They have to be encouraged to learn new things on their own, to kind of, I guess, interact directly with the content. And I feel so in order to kind of interest students in kind of the STEM areas, you have to show them that there is room for creativity in STEM. It's not just a bunch of technical facts, not just a bunch of kind of things they have to memorize. There actually is, they can explore the field. They can, they could potentially contribute to the field themselves.
So I want to come back to this in a minute, because I want to ask you, in terms of the number of students who choose to pursue STEM, does this traditional model play a role in your opinion? But I want to, before I ask you that question, I want to just bring up that the National Academies of Science and Engineering, along with the National Institute of Health, got together and back in 2010, 2011, really redefined what effective science instruction, or we could say STEM instruction, is. And I'd like to read that definition and get your thoughts on it. So this is the definition here, and it represents, I believe, a shift from the kind of image you see on the left to the image you see on the right. The definition is that effective instruction capitalizes on students' early interests and experiences, identifies and builds on what they know, and provides them with the experiences to engage them in the practices, or we could say skills, of science and sustain their interest. What do you think of that definition? Does that, especially thinking kindergarten through grade 12, is that a shift from your experience?
Yeah, I'd say that that is a shift, because it basically says that the students have to be able to kind of directly interact with the material themselves. They have to be able to learn about the material themselves. They have to be able to kind of get a sense of what STEM actually is for themselves. And I believe that the definition kind of better represents that necessity in education than kind of the idea that the teacher serves as a gateway between the content and the students.
So with that in mind, there's this kind of next generation model of instruction that's emerged, and one that we use for K-12 that replaces this traditional model, and it speaks, I think, to many of the points you brought up in our conversation so far, that I guess the elementary, middle school, and high school experience, where under a traditional model is much more maybe task and fact oriented and recall oriented. Here, the next generation model is really kind of putting the students and those skills together, so that the skills are actually a tool that the students use to develop and actually use the content or the disciplinary ideas and sort of the systems thinking, which is referred to now as cross-cutting concepts. And so the role of that teacher you described as a gateway under the traditional model isn't a gateway anymore. They're more somebody who's tuning the environment that a student learns in, whether it's a kindergartner, a 5th grader, or a 10th grader, or so on. And so helping students understand what it is to be a scientist, how to engage appropriately, and so on. You know, what would you say to K-12 educators who might prefer to play the role of an expert explainer and maybe more comfortable in a traditional model? What would you say to them? Do you feel like that this choice maybe between traditional and sort of next generation, or we might say, you know, recall and maybe something's a little more authentic, does it have an effect?
I would say that the perspective that the traditional model with the teacher as the expert creates is that STEM seems technical, it seems boring basically, where the student doesn't have any room to follow their own interests. They don't feel as though they have any room to create on their own, and which very it turns them away from STEM. And I believe that you need to have direct, I guess you described as cross-cutting concepts. The ability for a student to connect directly with the content, for the student to be able to explore on their own without to make sure that these teachers not, I guess, forcing a particular perspective or particular idea of STEM onto the students.
That's an interesting point, because under a traditional model, the content that students are exposed to is governed by the requirements of the state, but at the same time, it's really the teacher's perspective that students get. Would you agree with that?
Yeah, I'd say that's probably pretty accurate.
So I guess for society at large, and as we kind of wrap up, you know, there's a great deal of concern nationally about the future of STEM innovation, because STEM industry could use more qualified graduates, and not just folks with STEM degrees, but folks who have STEM degrees but also are as engaged as you seem in problem solving and using those higher order thinking skills. When kind of nationally these surveys are done asking students why they didn't go after a STEM degree, they often cite things like readiness for math courses, pure disinterest, or so on. What can educators do to change that? Why do you think so few students leave high school and go after a STEM degree?
I would say that the best thing that educators could do to make students interested in STEM is show that the STEM areas involve creativity. They involve they allow the student to explore. They're not these kind of static areas that you just have to learn and then kind of ignore them. They are fields which involve they're very diverse. They have many different components. Then there's room for students to make their own contributions to them. And I feel as though if educators gave more of that impression to students, more students would be interested in pursuing STEM degrees.
So it sounds like that interest is driven by the opportunity to really interact at some level and create.
Mm-hmm.
Well, I'd like to thank you, Josh, for joining us. I've learned an awful lot, and I feel like you're a great sort of example of how sort of this K-12 education experience leads up to college choices, but also this whole other dimension of workforce readiness and innovation. So I want to thank you for joining us.
Thank you for having me. It's great to be able to give some input.
You're very welcome. And I'd like to thank everyone who's joined us for this look at the path to innovation. If you'd like to explore the path to innovation further through the eyes of other STEM experts, please visit info.knowatom.com/upcoming-events. Thank you for your time. I'm Francis Vigent. Thanks for joining us.